Hello, everybody. I'm going to go over something that I would go over during class. It's not necessary for the lab, just one of those things Edgenuity threw in there, and I just want to make sure you get the right numbers for later if you end up taking more science courses in high school. So on the lab, so this is my lab sheet, and if you look, they give you the acceleration due to gravity as 10 meters per second squared. They probably use this number because 10 is an easy number to multiply by. So if you have 4.9, so here's your kilograms, you got to convert it to kilograms, right? But if you just multiply by 10, you move the decimal one place to the right, and you end up with that. So that's probably why they use the number 10, but it's not actually the number 10. And I want to go over that. I'm a big fan of making sure students get the right information. So let me show you how this works. And this is what I would have done in class. I can't really do it the way I would do it in class because I'm on a camera, right? But I think you'll get the idea. So here's a mass. It's already a predetermined mass. It's if you can see that, it's 500 grams. So we're going to be using the Newton's second law, the equation for Newton's second law. There we go. So force, hold on a second. Force equals mass times acceleration. Okay, now using my triangle method that I've been sort of trying to get you to use because it is a helpful little tool. I've got force equals mass times acceleration, right? So we're working with that. But we are actually going to focus on the acceleration number because that's what I'm going over right now is this number right here. So we're going to rearrange the equation where it's acceleration equals force divided by mass. Okay, so we're working with this, so force divided by mass is acceleration. So I've got my mass. This is my mass right here, and it says 500 grams. But again, I have to convert that into kilograms so I can put it in that equation, right? Which is what I've said before. It has to be in kilograms. So it's 3 places to the left, right? Which gives me 0.5 kilograms. Okay, so acceleration equals force, mass. I've got my 0.5 kilograms. Now I need to find the force. And force in science, in regular, American society, we would use pounds for weight. In the metric system and for the rest of the world, they don't use pounds, they use newtons. And that's a metric weight. Okay, so I've got my little spring scale here, and if you look, it has newtons on this side, grams on this one. We're going to forget about this side. We're not interested in grams right now. We've already got that. We're interested in the newtons. So this isn't a very accurate scale, but I think you'll get the idea. If I was to hang this from this mass from the scale, right, what I get on here is, so this is 4 newtons, right, this is 6 newtons. So each one of these lines is 0.4, okay, and it was right about here. So that would be 4.8 newtons, okay. So I'm going to go 4.8 newtons. Now remember, I'm going to take this unit and I'm going to make it kilogram meters per second squared. And if you don't know why, you can watch my other video that's below this one, and it goes over why I'm doing this, making the Newton unit that. But that's so I can cancel out the kilograms. Okay, so acceleration equals, and then I just bust out my calculator, which is over here. Okay, so I have my calculator. 4.8 divided by 0.5. Okay, I get 9.6. So I get 9.6 meters per second squared. Okay. Now, what does that number mean? Okay. That means this mass right here, if I was to drop it out of an airplane, now remember I measured the weight or the scale, right? It's gravity is pulling this, right? It's pulling it down with a force, okay? And that's the force right there, okay? Its mass is 0.5 kilograms. What I've just calculated is if I was to drop this out of a plane and it was to fall to the ground, it would, every second of time that passes, it would go 9.6 meters per second faster, okay? So just to make the number easy again, if I have 10, it would be, if I dropped it out of the plane, just to make the math easy, after 1 second, it'd be going 10 meters per second. Right? After 2 seconds, it'd be going 20 meters per second. After 3 seconds, it'd be going 30 meters per second. And that's what this number means. So for this one, if I was to drop this out of a plane, it'd be going, after 1 second, it'd be going 9.6 meters per second, and then plus 9.6. After 2 seconds, it'd be going 19.2 meters per second, and after 3 seconds, plus 9.6, it'd be going 28.8 meters per second, and as time, every second that passes, it would be increasing 9.6. Now, this isn't a very accurate scale, right? So it's not actually, this isn't actually the number either, okay? It's not 10, and it's not 9.6. I just want to show you how we calculate that. The actual number for Earth's acceleration of gravity is 9.8 meters per second squared. That is Earth's acceleration of gravity, okay? So I have just an example to, you know, put this into some sort of perspective. One of the assignments you would have done during our astronomy unit is calculate your weight, metric weight, which is Newton's, metric weight on other planets. Okay, so hopefully this kind of makes sense how this works. The moon's acceleration of gravity is 1.6 meters per second squared. If you've ever seen it, like an astronaut drop something on the moon, it falls slower than it does on Earth, okay, because it has less mass, and so its acceleration of gravity is lower, right? So if I was to calculate my weight here on Earth, I would go force equals mass times acceleration. I have a mass of about 200 kilograms. No, sorry, 100. 100 kilograms. The acceleration of Earth's gravity is 9.8 meters per second squared. So force equals 980 kilogram meters per second squared. So my weight, I'm going to put a little W here for weight, is 980 newtons. Okay, so that is my weight here on Earth, metric weight. Okay, so I'm going to put this off to the side, 980 newtons. Okay, now I'm going to do the same thing, but I'm going to calculate my weight on the moon. So same equation, force equals mass. My mass does not change. Okay, I'm still made out of the same stuff. Mass does not change. What changes, that changes your weight on different planets, is the acceleration of gravity. So the moon's acceleration of gravity is 1.6 meters per second squared. So force equals 160 kilogram meters per second squared, which is 160 newtons. Okay. Okay, so I weigh less on the moon than I do on Earth. Okay, and that's not changed at all. My mass stays the same. What changes is the acceleration of gravity. Okay. Now, what they're doing on the lab is this. So here's the table. Right, there's my table. Sorry for the jiggity lines. It's got a little pulley right here, and you got the little car. All right, there's my little car, and it's got a little hook, and it goes over, and then it has the washers down here. Okay, so the washers have a mass of, like, one washer has a mass of, I'm getting this from right here, 0.0049 kilograms. Okay, and gravity is pulling down with an acceleration. They give you the number 10. Just want to make sure that you know it's not 10, it's actually 9.8, but they're giving you 10. The acceleration is 10 meters per second squared. Okay, so we're going to calculate the force, how much the washer weighs and how much it's pulling down. So that's pretty simple. Force equals mass, which is 0.0049 in this situation. Erase my leg a little bit, times 10, which is nice because they, it makes the numbers nice, equals 0.049 newtons. Okay, so I've got a force pulling down. Erase this to get rid of all the junk. I've got a force pulling down of 0.049 newtons. Okay, that force is pulling here, it's pulling here, it's pulling here, pulling here. So what is the force that the washer is exerting on the car? Well, it's this one. It's this. It's 0.049 newtons, which is why this number and this number are the same. Force of gravity on the washers, right here, which I just went over. Applied force of the washers on the car, it's the same. The washer pulls down, pulls the string, and pulls the car forward. And with that, you've got a force and you've got a mass. Now you can calculate the acceleration, okay, which is what I went over at the beginning of the video. Okay, so you've got a force, you've got a mass, you can calculate the acceleration of the car, okay? But I just want to make sure that was clear. It's not actually 10, it's actually 9.8. They'll use the number 10, that's what they're telling you to do, fair enough. But just, Mercury is a smaller planet, right? Jupiter has a gravitational acceleration of 23.12 meters per second squared, which it's a big planet. It's really supermassive. So things are going to fall faster on Jupiter than they do on Earth. Likewise, if look at Pluto. Pluto's acceleration is only 0.72 meters per second squared because it's so itsy bitsy teeny weeny. Okay, so hope that clears it up. Just wanted to show you some stuff and how it relates to the lab and some stuff we would have done in class. Okay, I hope that helped out. Okay, take care, everybody.